Hi, my name's Hannah Slack, and I'm a PhD student at the University of Nottingham. And today I'll be presenting a talk on my research where I investigated the development of the Ford model in children. So in this talk, we're going to start off by covering what the Ford model is. We'll then talk about what's already known about how this model develops in children, what our hypothesis was, what we did, what we found, what it all means, and finally, what's happening next. So, what is the Ford model? The Ford model is an internal system that exists within the brain. It helps to control every movement that we make. For example, let's say that you wanted to turn on a light bulb. The brain will generate a motor command, and this motor command is essentially a set of instructions for the muscles on how best to move your body in order to carry out the desired action. For instance, here the motor command will say, "Hey, lift your arm towards the light switch, silly." So using what is known as an efference copy of this motor command, the Ford model then starts to predict the most likely sensory consequences of this action. So, what's most likely to happen when you flick on a light switch? Well, rationally, our brain will start to predict that we will see the light bulb turn on. So after this action has been performed, the comparator mechanism within the Ford model compares what we expected to happen, i.e. we expected to see a light bulb turn on, with what actually happened in our environment, i.e. information coming in from the senses about what we can see, hear and feel, etc. So if there's a match between the two, then we'll feel this little buzz feeling that tells us, I did that, I made that happen. And this feeling underpins our sense of self and what we're capable of in the world. And it helps us to navigate through life and achieve our immediate goals. So likewise, if there's been a mismatch between what we expected to see and what we actually saw, i.e. maybe we expected to see a light bulb turn on, but actually heard a stereo start playing, then we wouldn't experience this little buzz feeling. Instead, we'd start to theorize on what else might have caused what we've seen happen to actually happen, i.e. perhaps we flicked the wrong switch, or maybe somebody else turned on the stereo at the exact moment that we flicked the light switch. We then update our Ford model so that we can pick better actions next time, i.e. choosing a different switch, and this will hopefully result in the light bulb eventually turning on. So to recap, here's a graphical representation of this system. We start with the motor command, and an efference copy of this command is fed into the Ford model. The Ford model then forms predictions about what will happen as a result of that action, and then compares this prediction with what actually happened in our environment. So how does the Ford model develop in children? Well, if our Ford model is going to function properly, then we need to be able to have a mental representation about those action-outcome relationships. I.e., we need to know that flicking on a light switch leads to a light bulb turning on. We then need to apply this knowledge and select the most appropriate action that will lead to the outcome that we're after. We then need to learn to predict in real time what will happen as a result of that selected action. We then need to learn to compare our predicted outcome with the actual outcome. And finally, we need to learn to update our Ford model appropriately in response to new information. So previous research has shown that from 5 years old, children can understand action-outcome relationships and use this ability to refine, and this ability refines with age from 6 to 12 years old. For example, Soto et al. In 2020 showed children aged 6 to 13 years old images of hands at different rotation angles, and children had to imagine moving their own hand position to match the image on screen and judge whether the image depicted a right hand or a left hand, and respond once they had done this. And it was found that children aged 6 to 9 years old demonstrated reduced accuracy and longer response times compared to older children. And this suggests that children's understanding of these action-outcome relationships improves with age throughout childhood. So similarly, previous literature has also shown that from 5 years old, children can plan the outcomes of their actions, and again, this gets more accurate and efficient with age from 6 to 12 years old. For example, Brink et al. In 2020 asked children aged 5 to 12 years old to grasp and rotate a hexagonal knob to various degree angles. And in this task, children have to predict how best to grip the apparatus and rotate it in order to arrive at the optimal end state. It was found that all children could complete this task when the required rotation angle was easy, i.e. just rotating it 160 degrees. So young children do have an ability to plan their actions and predict the end state of their movement, so where their hand will end up. However, the reaction time decreased with age for every rotation angle that was tested. So this suggests that motor planning becomes more accurate and efficient as children age. So finally, the ability to update the forward model also appears to develop as children age. So it develops rapidly between 6 to 7 years old, remains stable from 8 to 12 years old, and then continues to develop from 12 to adulthood. So Wilson and Hyde in 2013 showed that children aged 6 to 12 years old and young adults a horizontal touchscreen. Participants began with their finger at the starting location at the bottom of the screen. A target then appeared in one of 3 positions. Participants had to touch the target as fast as possible, and on 20% of trials the target's location altered after the participant had begun to move. These are called jump trials, and you can see an example of that on the right of the screen. So on these trials, the time taken for participants to correct their movement trajectory was recorded, and it was found that children aged 6 to 7 years old were slower to correct their reaching trajectory compared to children aged 8 to 12 years old, and those aged 10 to 12 were slower to correct their movements compared to adults. So this suggests that the ability to update the forward model in response to new information improves as children age. So overall, it seems that the forward model system forms early on in childhood and then refines with age as children grow. But research into this area is incredibly limited. So in my research, I'm predicting that efficient use of the forward model system would be predicted by age, with older children showing better performance than younger children. So what did I do? Well, I recruited 43 children. This is 26 males, 16 females, and 1 preferred not to say, and they were aged 4 to 12 years old. They were asked to play an online computer task where they were presented with 2 race cars and a set of traffic lights. So participants had to click the screen as soon as the green light was visible, and the faster that they clicked, the greater their chance of winning the race, and their reaction time was recorded relative to the onset of the green light. So here's a demonstration of this task. You can see that the participant needs to click the screen as soon as the green light is on the screen. And the faster they do this, the better their chance of actually winning a trial. Okay, so in this task, you can either have an anticipatory response or a reactive response. An anticipatory response occurs when you begin to prepare to respond whilst the amber light is still on the screen. To do this, you need to hold a prediction about what the outcome of your response will be. And if it so happens that you've clicked at the wrong time, then you need to integrate that information, update your forward model, and click a different time on the next trial. Whereas a reactive response happens when you wait until the green light is on the screen before responding. So this type of response does not require any predictions about what will happen as a result of your response. You're just responding to something flashing up on the screen, so this does not require your forward model. Okay. So using an equation defined by Burnett, Hayes et al. In 2012, I classified responses as a result of either an anticipatory or reactive decision-making process based on participants' reaction time distributions. The figure here depicts these 2 different types of responses. The horizontal line is the response threshold, and this needs to be reached in order for an action to be executed. The orange slope is the anticipatory decision-making process, and this is triggered by the amber light and rises slowly towards the response threshold. The green slope shows the reactive decision-making process, and this is initiated in response to the green light and rises sharply towards the response threshold. So for this equation, we can see that the mean rate of rise in participants' anticipatory and reactive responding. So I conducted a stepwise linear regression on the mean rate of rise in anticipatory responses with the factors age, parent-reported impulsivity, and sex. So the mean rate of rise in anticipatory responses was significantly predicted by age and was not predicted by parent-reported impulsivity or sex. So this suggests that as age increases, the mean rate of rise in anticipatory responses also increases. So, as children get older, they're more likely to start predicting when best to respond. Okay, so one criticism here might be that, well, perhaps this could have occurred simply because the older children respond faster in general. They just have a faster reaction time compared to younger children. So I conducted a partial Pearson's correlation of the mean rate of rise in anticipatory responding as a function of age, controlling for mean reaction time. So there was a significant positive correlation between the mean rate of rise in anticipatory responses and age. This suggests that older age was associated with faster anticipatory responding, irrespective of participants' average response speed. So I then conducted a stepwise multiple linear regression with the factors age, parent-reported impulsivity, and sex on participants' mean rate of reactive responses. So the mean rate of rise in reactive responses was not predicted by age or parent-reported impulsivity. However, this was significantly predicted by sex, with females responding more reactively than males, and this suggests that as the mean rate of rise in reactive responses this suggests that the mean rate of rise in reactive responses is unaffected by age. So what does this all mean? Well, it appears that the Ford model system develops with age, with more predictive responding as children grow. So older children show better use of their Ford model system than do younger children. So what's next? Well, limited research has investigated how the Ford model develops in adolescence. Wilson and Hyde in 2013 also noted that the Ford model undergoes continued refinement between childhood and young adulthood, and the pattern of this change warrants investigation. Similarly, adolescence is a developmental period marked by maturation in the brain areas thought to underlie the Ford model, such as the frontal and parietal cortices. Adolescence has previously also been associated with the onset of certain pathologies that have shown an impaired Ford model, such as schizophrenia. And again, dopamine has been shown to be important for detecting errors between the predicted and observed actions. So adolescents show a lower presynaptic dopamine level compared to adults. So taken together, this all suggests that adolescence is crucial for Ford model development, yet no one has studied how the Ford model develops during this period. And this is something that I'm going to be working on with local schools in the Nottingham area. So in addition to that, previous studies have also shown that people with Tourette Syndrome struggle to update their Ford model. And this has been under-researched. So Tourette Syndrome is a movement condition where people experience sudden movements or vocalizations known as tics. So tics are believed to result from an overabundance of dopamine in the brain, leading to tonic stimulation of postsynaptic dopamine receptors. And as we've seen, dopamine has been said to play an important role in the Ford model system. So I'll be working with the charity Tourette's Action to investigate how the Ford model develops in adolescents and young adults with Tourette syndrome. So that's all from me. Thank you for listening, and you can find my contact details on the right of the screen. I look forward to hearing any questions that you have.